Okay. So yeah, I said that I'd have the homework up by yesterday, but I don't have it up by today. I would have had it up by today's lecture if I had the pressure of today's lecture to do that, but unfortunately I needed all the time to prepare for this one. So if I were actually done preparing the lecture like half an hour before this, I would have done that. I will try and do so tonight. And in the worst case, it'll be up by the start of tomorrow's lecture. So I'm going to change one. I'm going to add one problem, and then there's a known typo. That's the modifications to the assignments as it stands. And the known typo is x to the x should be e to the x. Okay, so first off, we're going to continue discussing second order ODEs, second order linear ODEs. And so I'm going to state a general results. So suppose that you have the equation y prime prime plus f of x y prime plus g of x y equals 0. So the homogeneous equation. If we have that f and g are continuous on some interval, so in particular, if f and g fail to be defined, then the theorem would only apply to intervals in which they are successfully defined. So if f and g are continuous on an interval I, then the space of solutions to this equation is a two-dimensional vector space. What does this mean? That means that there are solutions y1 and y2 such that neither is a multiple, such that neither is a multiple of the other. And the general solution is of a form of a linear combination of these two. So this is a very, very general results. And it says what the solution space to a homogeneous equation looks like, so long as f and g are defined everywhere where we are working, and so long as they're continuous. And that's like a very generous set of assumptions. Now, I suspect that the book in which I'm using might be lying. And so it might be continuous and something like locally Lipschitz. But you can ignore that hypothesis. This is a technical thing. Okay, so with respect to this cool general results, which I'm just going to quote, what do we have? Well, in particular, does anyone have any questions about what that general result means? Okay, so suppose the equation is is a constant coefficient equation. For A, B, C real numbers, and A does not equal to 0. So that it actually is a second order equation. Then we had the ansatz last time. Try y is equal to e to the tx. And when we did that, we plug this in, and then when we differentiate e to the tx, we get a t outside, and that's just a number. We got a t squared e to the tx plus b t e to the tx plus c e to the tx equals 0, which gives us that this only happens because e is everywhere strictly positive. That's a p squared plus bt plus c is equal to 0. So in other words, t is the root of this equation. And if t is the root of this equation, we can check that we will indeed get a solution. And so then we have several cases. Case 1. Suppose the equation a lambda squared plus b lambda plus c equals 0 has two distinct real roots. T1 and T2. Then e to the T1 x and e to the T2x are solutions. And by the results, by the theorem, because neither of these is a multiple of the other, because T1 and T2 are distinct, then by the theorem, all solutions have the form C e to the T1x plus D e to the T2x. So that's case 1. Now, case 2. So let's imagine that we have, and by the way, I can tell you exactly when case 1 happens. So case 1 happens when b squared minus 4ac is strictly greater than 0, right? Case 2 is going to happen when b squared minus 4ac is going to be less than 0. This is the case where we have imaginary roots by the quadratic equation. Suppose lambda squared, a lambda squared plus b lambda plus c equals 0 has a pair of complex conjugate roots. And I'll write the roots as alpha plus or minus I beta for beta does not equal to 0. So if the coefficients of the equation start off as real, then all complex roots have to come in conjugate pairs. And this is just directly from the quadratic equation. Because you have the real part and then you have the radical, and that's purely imaginary. And so the plus or minus is just the purely imaginary part, and the b squared divided by 2a, that's just the real part. Um, cool. So what happens now is, well, e to the alpha plus I beta x and e to the alpha minus I beta x are solutions. But these aren't real. And that's a bit of a problem because we want the space of solutions to this equation in terms of real things, because this is the space of real solutions implicitly when I talk about the general results. So what are we going to do? Well, if we have something like e to the alpha plus I beta, we can rewrite this as, let's say x, as e to the alpha x, and then we have e to the I beta x, but I beta x becomes cosine of beta x plus I sine of beta x. So as a consequence, if we have some linear combination c e to the alpha plus I beta x plus d, where c and d are at the moment going to be imaginary. Sorry, not imaginary, complex, but possibly. Then what we can do is we can rewrite this as well, sort of the e to the alpha would be, x would be outside. And then we'd have c to the, well, c times cosine alpha x plus I sine beta x. Sorry, both of these are beta. And then you'd have the cosine, because now we have the minus sign, and cosine of negative beta is, or sure, I'll write it as minus beta x for the moment. And then plus I sine minus beta x. Now, using these functions are even and odd, we get e to the alpha x, and then we get here, in general, c plus d cosine beta x. And then I times c minus d sine beta x. Now, if we let's call this star. If we let A equal C plus D and B equal I times C minus D, then in general, the data of specifying A and B is the same as specifying the data of C and D. So we can there are two unknowns here and two unknowns here, and they're like not redundant equations. So if you have C and D, you can solve for A and B, and conversely, if you have A and B, you can solve for C and D. So in general, then our equation just becomes and now I'll actually distribute the e to the alpha x. So I'll write A. Do I want to put the cosines before the exponentials? What looks nicer? I guess, what did I write? I wrote the exponentials before the cosines. I guess that makes sense aesthetically. So what's the takeaway message? The takeaway is that e to the alpha x cosine beta x and e to the alpha x sine beta x are linearly independent solutions. So neither is a multiple of the other. Linear independence does not in general mean that two things are things are not multiples of each other if there are multiple things more than two. But if there are two things, then it's the case that the condition just reduces to neither being a multiple of the other. But if you have three things, sort of, it's it's more interesting. So in particular, for example, in two dimensions, what linear independence means is that 2 points are going to be linearly independent only when they do not lie on the same line passing through the origin. So for example, if I have this point and this point, then neither is a multiple of the other, because if you look at all multiples of this point, it's this line, right? And if you look at all multiples of this point, it's this line. And you can see that these lines only intersect at 0, so you can't in particular get this point on this line. Whereas in 3 dimensions, the statement would be that there is in general no plane through the origin containing all 3 points. But you could have 3 points not be on the same line, but still be in the same plane through the origin. So that's why the condition is more general in higher dimensions. But in 2 dimensions, it's just the matter of what each not being a multiple of the other. Well, anyway, because neither of these is a multiple of the other, then the general solution is c e to the alpha x cosine beta x, and I'm going to use c and d as my usual coefficients. Okay, so the point is that we found 2 linearly independent solutions, therefore we know what all of the solutions are, right? And here we found 2 linearly independent solutions, therefore we know where all of the solutions are. Here, the process was longer because we found solutions that weren't real, whereas we only care about real solutions. So we had to use some complex trickery in order to actually produce real solutions in the first place. So like, as far as we care for real solutions, these weren't real solutions, so we didn't solve the problem when we got there. We had to go down to here to actually solve the problem. Okay, and finally we get to case 3. And so in case 3, it also is dependent on the discriminants, and I guess it's the leftover case. So in this case, it was b squared minus 4ac is strictly greater than 0. In this case, it's b squared minus 4ac is less than 0. And in this case, it's that it's exactly equal to 0. And so this is the case lambda a lambda squared plus b lambda plus c equals 0 has a repeated, or I'll say a double, or a multiplicity 2, maybe. Real roots. And by the quadratic equation, it would necessarily be real. Okay, so then what happens? Well, if this root is t, then e to the t x is a solution. Because in particular, t is a solution of the characteristic polynomial. This is called the characteristic polynomial of the equation. Is that a good name? Yeah, sure. So we have one solution, but the problem is that by this theorem, we know that there has to be a solution that isn't a multiple of this, such that the solution space is all combinations of those two things. So the question is, where do we find the second solution? And I have two very related ways of getting this. And then later on, we'll do a different way of getting this. So suppose the equation was, and let's imagine that A is 1 for a second. Let's just forget about A. Suppose the equation was lambda minus, because it's the same equation if you scale everything. So we can just make A be 1 because A is non-zero. So suppose you have lambda minus t times lambda minus t star is equal to 0 for t star does not equal to t. Then e to the tx and e to the t star x are solutions. Thus, so is e to the, let's see, I'll do t star x minus e to the tx divided by t minus t star. Sorry, t star minus t. Now we're going to take the limits. Limits as t star goes to t. So what we get is that the limits as t star goes to t of e to the t star x minus e to the tx over t star minus t. Now, if we plug in t star equals t, we get 0 divided by 0. So we can't do that. However, if we plug this in and we get 0 divided by 0, then what rule applies for finding this limit?
L'Hopital.
L'Hopital, yeah. So by what L'Hopital's theorem says is that if you are taking a limit of two functions and both functions are 0 at the point at which you want to take the limits, then it's the same as taking the limits of the derivative of these two functions. And we're taking, so t is now going to be fixed, and we're taking the derivative with respect to t star. So x is now a constant. X is just a number. And if we take the derivative with respect to t star, well, e to the tx is just a number, and e to the t star, we get x, e to the t star x. And then if we take the derivative of t star, we get 1. And here we can plug in t equals t, t star equals t. So we get x e to the tx, right? And I can also do another thing. So here I considered solutions t star approaching t with both of them being real. Here's another way to do this. Consider lambda minus t, and now we're going to do plus I beta and lambda minus t minus I beta. So now we're going to, instead of making it be two distinct real roots, we're going to make it a conjugate pair of complex roots. Then in particular, we know that e to the t times sine of beta t is a solution. And this is for beta does not equal to 0. I mean, yeah. Thus, also, we're not even going to consider the cosine solution. We're just going to consider e to the t sine beta t divided by beta. And then we're going to take the limits as beta goes to 0 of e to the t sine beta t divided by beta. So this is then by L'Hopital, we're going to take the beta derivative of this, which is going to give us a factor of t. So it's going to be limits as beta goes to 0 of t e to the t cosine beta t divided by 1. And we can plug in beta equals 0, cosine of 0 is equal to 1. So this is t e to the t. Sorry, there's an x here everywhere. That's just a number otherwise. Okay, so we have done this L'Hopital trick and we've suggested that in the limits, sorry, this should not be t, this should be x, because I'm taking the t derivative and x is the constant. Good. So let's actually check that this is a solution, because it looks like in the limit it's a solution, but does this argument even make sense? First off, if a is equal to 1 and t is a double root, then the equation is lambda squared minus 2t lambda plus t squared is equal to 0. So this is the thing that factors as lambda minus t squared, right? Consider, I guess, ansatz. So this correspondence to the equation y prime prime minus 2 t y prime plus t squared y is equal to 0. So consider the ansatz y is equal to x e to the t x, right? Then what is y prime?
X squared e to the tx.
This is with respect to x, not with respect to t. So t is just a number.
So it's tx e to the tx.
Yeah, so if you differentiate this, then you'll get tx e to the tx, but we also have to do chain rule, don't we, right? So we get another term. What's the other term? So we just differentiate the x, so we also get e to the tx, right? So when we differentiate the x, in fact, I'd write these terms in the other order usually. Okay, what's y prime prime? So we differentiate this again with respect to x. And so what do we get?
Well, the first one is just t times. Oh well, okay. So t squared x e to the tx plus t e to the tx.
Yeah. And then what do I get when I differentiate this?
Just x e to the t.
Yeah. Rather t e to the tx, right? So that's t squared x e to the tx plus 2t e to the tx. Okay, so let's plug this into the equation. So the equation becomes y, sorry, y prime prime minus 2 ty prime plus t squared y, and that's going to be, so t squared x e to the tx plus 2t e to the tx, then minus 2t times y prime, so minus 2 t squared x e to the tx minus 2t e to the tx, and then plus t squared x e to the tx. And so if we look at this, we have this term minus 2e to the tx and minus 2e to the tx. So these two terms cancel out. And here we have minus 2t squared x e to the tx, and then we have two copies of t squared x e to the tx there. So that's in fact 0. So it is in fact a solution. So it is a solution, but there's actually a better proof. And the better proof is, let's D denote the differentiation operation with respect to x. Then y prime prime minus 2t y prime plus t squared y can also be given as, well, we're going to take the differentiation operation squared. We're going to take minus 2t times the differentiation operation, and then we're going to just take t squared times the identity operation, and we're going to apply that onto y. But the left-hand side factors as d minus t squared y, right? So this calculation, we had to differentiate a bunch and it was boring. Let's look at d minus t squared of x e to the tx. First off, that's d minus t, and then let's apply one copy of it. So when we differentiate this expression, we get e to the tx plus t e to the tx, right? And then we subtract t times this. Sorry, there's an x here. So that cancels out. And so we just get d minus t of e to the tx. And that's going to equal, so when we differentiate e to the tx, we get t, why am I writing that? T e to the tx. And then we're going to subtract t e to the tx. And so that's 0. And so notice that this calculation right here, it was much easier to do than this calculation above here. So this idea is that we can represent this thing as being some differential operator.
That assumes that it's like distributive.
So the thing that happens is that differentiation commutes with the identity and multiples of the identity, right? Because everything commutes with multiples of the identity. So in general, the commutativity is the key property. If, for example, this involved D and S, where D and S did not commute, where they were two distinct differential operators, then we would not be allowed to do this factorization. But because D commutes with itself and because D commutes with the identity, this makes sense. So that's the only reason that that happens. And so we can consider this as then being factored as two operators. Well, you apply this operator twice onto y. That's another way of seeing it. And so, yeah, that was a cool calculation. And again, this is sort of I justified in some very high level why this factorization is legal. But if you don't believe me, then we had this calculation here, which was a bit more tedious. But what's the lesson? We're talking about case 2, repeated real roots. The point is that with this L'Hopital method, and then verifying that what we got actually makes sense, we found solutions. Thus, e to the tx and x e to the tx are linearly independent solutions. Thus, the general solution by the theorem is c e to the tx plus d x e to the tx. And so that completes all 3 possible cases. The 3 possible cases were based on what the value of the discriminant was. It was bigger than 0, less than 0, or exactly equal to 0. And in all 3 cases, we found 2 linearly independent solutions that were real. And therefore, we got the space of all possible solutions if we believe the theorem that I said at the beginning of class. So we can do a bunch of examples now, but all of these examples are going to be super quick. Any questions about this? Okay, so let's do a bunch of super quick examples. So let's consider y prime prime minus y is equal to 0. So this is a constant coefficient linear second order homogeneous equation. That was a bunch of words. What's the characteristic polynomial in terms of lambda?
T squared minus 1 equals 0.
Yeah, in terms of lambda, I'll write lambda squared minus 1 is equal to 0. But instead of writing equals to 0, I'll just factor it. How does it factor?
Lambda minus 1 times lambda plus 1.
Good. Difference of squares, right? So thus, the general solutions, well, solution, I'll write, is what?
I guess e to the it's equal to 1 or minus 1. Oh, so it's e to the minus x and e to plus x?
Well, so it's going to be a linear combination. So we're going to write c e to the, now, you wrote this root first. This root is plus 1, right? So let's write plus 1 first, since that was the first factor. So that's plus 1 times x plus d, and now this is the root minus 1, e to the minus x, right? Cool. So let's consider y prime prime minus 5y prime plus 6y is equal to 0. So we're going to consider lambda squared minus 5 lambda plus 6. And this is something that can be factored by inspection again. You don't need the quadratic formula. What are the factors?
Lambda minus 3 times lambda minus 2.
Good. Why? Because you want 2 numbers that multiply to 6 and such that when you add them together, you get -5. So -3 and -2, they sum to -5. So that works. Cool. So the general solution is okay, it's pretty much the same thing as before. C e to the 3x plus d e to the 2x. Okay, now what about y prime prime plus 2y prime plus 2y is equal to 0. So we consider lambda squared plus 2 lambda plus 2. And now I'm going to say equals to 0 because in general, when I sort of have these complex cases, I actually like to use a quadratic formula. So the quadratic formula tells me, plugging in the numbers, that lambda is, how would you read it off with these numbers?
Two plus or minus I.
-2. Oh, well, so it would be -2, right? Just writing it out. Plus or minus what? The square root of what?
Oh, 4 minus 8.
Yes.
So -4.
And then divided by 2. And so that's, well, that's, we get -4. So that's 2i, and then there's 2's everywhere. So we get -1 plus or minus I. And so thus, the general solution is what? C times something. What's the something?
Would it be x plus I?
Just this?
No, e to the x plus I.
Oh, okay. Well, it would be -1 plus I guess, x, but that's not real.
Oh, okay.
What's the real solution?
Oh,
So there's a -1, so we're going to do minus x times what?
Sine 1.
Back
Sine x.
to the section. So if the roots were e to the plus or minus I beta, then the solutions would be this, right? E to the alpha x cosine beta x and e to the alpha x sine beta x, right? So in our example, what does that become?
So c times e to the x times cosine of x.
Yeah, because beta is 1, and it's e to the minus x because we have a -1 here. Plus d times what?
It's the same thing, but with sine.
Yeah, exactly. Okay, so that's the general solution. So that's how complex cases work. And I guess as just a final example, what if we have y prime prime minus 6y prime plus 9y is equal to 0? So we consider lambda squared minus 6 lambda plus 9. And can anyone see how that factors?
Lambda minus 3 squared.
Yeah. So this is minus 2t and this is t squared. So what happens then is, yes, so we have a repeated root. And now, so the general solution is what?
C e to the free t plus
Mhm.
cx e to the
Well, d is our coefficients. And then, oh yes, 3tx, x e to the 3tx, right? Sorry, there's no t. What we said t. I wrote t because we meant to say x, right? Let me just check that I don't have t in any of my other final solutions. No, the t is just, it's not part of it. It's x. They're functions of x. Okay, cool. Okay, solving constant coefficients second order homogeneous equations is easy. It's solving the quadratic equation and then writing something down by prescription, right? So any questions?
Yeah, so I'm just confused on why there's an X for the D. Like,
Right. So we have a repeated root, right?
yeah.
And we have this theorem saying that in general, there's going to be two linearly independent solutions, and it's going to be combinations of those two linearly independent solutions, right?
Yep.
So we were talking about case 2. What if we have double roots? Sorry, case 3. Well, then we know if the root is t, that e to the tx is a solution, right?
Mhm.
But there has to be one more solution. And so the question was, what is that other solution? And so then we went through two processes of using L'Hopital's rule to show that in the limits, in the non-degenerate examples, we got this expression, x e to the tx. And then we verified that that was actually a solution. And so what happens then is that we found a second solution. And by the theorem, because we have two linearly independent solutions, all solutions must be multiples of those two solutions. And that gives the full solution space.
Okay. All right. Thank you.
No worries. Okay. And so now I'm going to do a thing that's almost as equally easy as that. I mean, so what was easy and what was hard? Solving the sample problems is easy because it's the quadratic equation. The theory is actually a bunch of theory, and it's good to know this theory and where this comes from. So now I'm going to talk about something called Euler equations. And what an Euler equation is that it's an equation of the form a x squared y prime prime plus bx y prime plus cy is equal to 0. So we took the previous equation and we had constant coefficients, but now it's not constant. Now it's not constant in a very special way. This is a multiple of x squared and this is a multiple of x. That's how we've changed the solutions to not be constant, only in this very subtle way. And so there's a trick for solving these. What you do is you consider the expression x, y prime, and you consider differentiating this. And so what do you get if you differentiate this?
y prime plus so then it's just xy prime.
Double prime. Yeah.
Yeah.
Cool. So what happens then is that x, this original equation, well, in particular, this implies that xy prime prime is equal to xy prime prime minus y prime. So here we have a x, and then we have x times y double prime. So that's equal to x y prime prime minus y prime. plus bxy prime plus cy. And so that gives us a xy prime. And then this becomes plus b minus a x times y prime. So we have the same expression here, plus cy, right? So now we're going to do something pretty wonky. We are going to I am definitely going to run out of notes for today. With the second break will be a long break while I prepare some last minute examples. Yeah, I have no, I'm going very quickly through my notes. I did not expect that. Anyway, so xy prime, there's another way to write that. We can write this as x dy dx, right? Now, if we consider the expression differentiating the logarithm of x with respect to x, then what is that? What's the derivative of log?
1 over x.
Yeah. And so as a consequence, d log x, this totally 100% makes sense, I promise you. It's dx over x, but here we have x over dx. So this is in fact dy over d log x. And similarly, when we have the expression x times xy prime prime, then what that is equal to is it's equal to x times dx of xy prime, which is dy d log x. But here we have x over dx. So this is in fact equal to d squared y d log x squared. So you'd write, I guess I'll write parentheses here to just indicate it like that. Okay, this 100% makes sense. It's good. Right. So what happens then is we have this equation, ax times xy prime, sorry, there's a prime here. And so that becomes, if we now rewrite everything, substituting t is equal to log x, the equation becomes so now we're going to imagine that y is a function of t. Well, then this expression right here is nothing but y prime prime with respect to t, no, instead of with respect to x. So now we're taking t derivatives. And so this becomes a y prime prime plus b minus a y prime plus cy equals 0, where derivatives are with respect to t. So we basically can consider them as functions of t. Now, y is an unknown function of t. So if y of t, let's say y1 of t is a solution of this equation, then what happens is that y1 of log t, log x, rather, is the solution of the original equation. So as much as I assured you that this 100% made sense, it does look a bit suspicious. So what then can we actually do to unsuspiciousify this? Although it is currently 57 minutes, so I will leave it at this as for being suspicious. And let's take a break until 3 minutes plus 13-minute break, 7:10, resume 7:10. Okay, so let's get started again. Okay, so we did this very suspicious thing. We're working with Euler equations. And what are we going to do to sort of sanity check that this d log thing was good? So the solutions to that equation are, well, if t is a root of let's say a lambda squared plus b minus a lambda plus c, then e to the t u, where we've now have u as y, should be a solution of the equation above. So when we substitute this, e to the t log x is equal to x to the t, should be a solution of the original equation. And so what happens then is we go back to the original equation, which was a x squared y prime prime plus bx y prime plus cy is equal to 0, and we use the ansatz. So all of this process was for coming up with the ansatz that we're going to use. And before we use the ansatz e to the t x, now we're going to use the ansatz x to the t. Then gets. So y is equal to x to the t. What happens when we plug in x to the t here? So it's going to be really interesting. When we differentiate x to the t twice with respect to x, where t is a number, what do we get?
T times t minus 1 times x t minus 2.
Yes, and so we get times x squared times x to the t minus 2 because we differentiated twice. So now you see why there was an x squared there, right? So it's just exactly to cancel with the two derivatives. It compensates for the derivatives and it goes back. And then for the next coefficient, what do we get?
Bx times t x to the t minus 1.
And then plus c x to the t. And so, yes, the x's all line up. So what happens is that we get a times t minus 1 plus b times t plus c, all times x to the t. And so if that's equal to 0 everywhere, then that implies that t is a root of let's say a lambda times lambda minus 1 plus b lambda plus c, and that's equal to a lambda squared. Sorry, this is plus b, there should not be minus, plus b minus now a lambda, so a lambda plus c, which is the equation that we got before, right? So that says indeed that if we solve this equation, which is just we take the first coefficient and we subtract it from the second coefficient, so that's how we modify the equation, and we find roots of that, then z's or x to the power of t, where t is a root of that equation, is going to be a solution of our original Euler equation. Okay, so the question is, well, what happens if we have double roots? Or what happens if we have complex roots for that matter? Well, let's do double roots first. And let's do the same L'Hopital approach that we had before. If the equation, so if we have solutions x to the t1 and x to the t2, then x to the t1 minus x to the t2 divided by t1 minus t2 is a solution. So in the limits, and this is going to be a bit interesting. We're going to take limits, t1 goes to t2, so t2 is going to be a constant in this case. X to the t1 easier than writing it again. Now we're taking the derivative with respect to t1 by L'Hopital. How do I take the derivative of this expression, x to the t1 with respect to t1? How do I rewrite x to the t1?
Like e to the e to the log x t1.
Yes, exactly. And remember that x is just a number, so log x is just a constant. So when I differentiate this, what do I get?
Log x e to the log e to the log x t1,
Which I can just rewrite as
x t1.
And then the derivative of t1 is 1. I guess, sorry, I need to keep the limits there. It is bad to drop limits before you're ready to drop limits. This is limits. T1 goes to t2. And now I can just plug it in. So I get log x, x to the t2. So if t2 is my double roots, then I should have this as my solution. Now I can check that that's a solution and it's indeed the solution. And remember from before, if u e to the tu was a solution, then there's another way of seeing it. Then for u equals log x, I'd exactly recover the solution that I had above. So we didn't have to do the L'Hopital thing again, but I thought it was pretty cute because we had to differentiate this with respect to t1, and it was interesting as to how you did that. So that's why I did that. No, it's t. Yeah, x to the t. No, exactly. Okay. Now, what about complex roots? Well, we're going to do the same thing that we did in the second example. If a u e to the u, rather a e to the alpha u cosine beta u plus b e to the alpha u sine beta u are solutions. Then when we plug in u equals log x, I'll get a times x to the alpha. And then here I'll get cosine beta of log x. And that doesn't simplify. So you have logarithms and cosines, and that's a fact of life. If you have complex solutions, then you're of this augmented polynomial, then it is a reality that the solutions of the Euler equation will have logarithms inside of cosines and sines. So solving Euler equations is in fact just as easy as solving the homogeneous first order constant second order constant coefficients equations. Because all that you do is you solve quadratic and then you write down the answer, except the recipe for writing down the answer is a bit different. So let's do some examples. I have to add some color because if it's just red, then when you look at the notes, it doesn't look good. Like there's too much red. So you eventually have to underline some things. So let's look at something like x squared y prime prime minus 2y is equal to 0. So we are going to consider a polynomial. And what polynomial is that going to be in terms of lambda?
Is it just
So- Okay.
is it just like lambda squared minus lambda equals 0?
Yes. So the idea, well, I mean, you have the -2 here still, right? So -2 equals 0, right? You don't just drop this. But what happened is there was a 0 term here. So this was, in fact, the polynomial x squared y prime prime plus 0 x y prime minus 2 y, right? And so what we did is we took this one here, I guess. And we subtracted it from here. And so we got a -1 here instead, because that's the process for doing these things. When we started with this equation, a x squared y prime prime, b x y prime cy, we rearranged it to get the equation a x, now some transform thing, b minus a, and then c. So b changed to b minus a. That's the key point. So this is the polynomial that we consider when working with this equation. And well, so instead of writing equals to 0, how do I factor this?
Lambda minus 2 times lambda plus.
Well, okay, I think you said 1. I cut off at the end. But anyway, yes, that's correct. So that's the factorization. So these are two distinct roots, and the roots are going to be 2 and -1. So the general solution is what?
X squared and x minus 1.
Yeah. But the way that you say it is c times x squared plus the x minus 1. Yeah. Good. So Sure. Okay, now we're going to work with x squared y prime prime minus 3 xy prime plus 4y is equal to 0. So we consider, what do we consider in terms of lambda?
Lambda squared minus 4 lambda.
Mhm.
Plus 4.
Exactly. And can you see how to factor that?
Just lambda minus 2 squared.
Good. So we have repeated roots. And so remember, when we have repeated roots, we add a logarithm in front of our x to the t. So I'll just say it. It's c. Now the root is 2, so it's x squared. And then you'd have d. And then what you'd have is that now you add a logarithm. Actually, for aesthetic reasons, the logarithm follows the x squared. So for example, in computer science, you say an algorithm has runtime n log n, right? But you'd never say that an algorithm has runtime log n. That's bad. It's n log n. That's the way it has to be, right? For aesthetic reasons, you write it in that order. It's like in English, what's the very famous sentence? Let me look up the famous sentence. Well, okay, there's a sentence that just uses all of them. Does it give an example? All of these, it's memes that have the anything. Anyway, so colorless green ideas sleep furiously. Colorless green ideas, it has to be in that order. If you say green colorless ideas, or no, well, I mean, those are only 2 adjectives. There are chains which are much longer, and so, oh, here is the meme. Okay, I have found the meme. So you have a lovely little old rectangular green French silver whittling knife. But if you say it in any other order, the adjectives are wrong. It sounds wrong because in English, there's this incredibly complex rule that native speakers just happen to know about how to order adjectives in terms of categories. Because it just sounds weird if you do it otherwise. Well, in math, there's sort of a similar conventional rule about how you write expressions. And the logarithm will always have to go after the x. Anyway, I digress. Okay, so let's do the next example. What if we have something like x squared y prime prime plus xy prime plus 4y is equal to 0? So what the equation that we consider is what?
Gamma squared plus 4.
Yes, so it's 1 and 1 here, so that becomes a 0. And then we get plus 4 equals 0. Well, okay, this we can actually factor it. because it is a difference of squares, but except for the fact that it's a sum of squares. So in fact, what you get is lambda what?
Plus 2i minus 2i.
Yep. Let's say that the repeated root is 2i and not negative 2i, just to make the signs be a bit nicer. So when that happens, this is an example of a purely imaginary equation. So our thing is going to be 0 plus or minus 2i. So if we look at what the solutions were, it was x to the alpha. Well, alpha is 0, so it's just going to be thing. So it's going to be cosine and sine. Beta is going to be 2, so cosine 2 log x. Let's say c times cosine 2 log x plus d sine 2 log x. And like that's indeed the solution to this equation. If you have something like this, it's this. So I mean, it's sort of interesting how just changing these coefficients up a bit, you get pretty different forms of solutions. Because here it was x squared log x, but suddenly you have logs inside of cosines. Well, why is that? Why did, well, it's because exponentials, when they become complex, change into sines and cosines, because there's a very intimate relationship between the exponential and sine and cosine. So that's sort of where that comes from. Okay, now, and for our last example of this, we're going to consider x squared y prime prime minus 3xy prime plus 5y is equal to 0. And so we consider what equation?
Would it be minus 4 lambda plus 1?
That's 5 that I wrote.
Oh, 5. Oh, okay. So plus 5.
And do you see how I can factor that?
Would it be lambda minus 5 plus 1? Minus
Yeah.
4 lambda.
So we want the 5 to be negative because that gives us the -4, and then we want the 1 to be positive. So that's right. Sorry, we did something very wrong. This does not have real solutions. This would make sense if we had -5 here, right? But it's a +5. So let's actually use the quadratic equation. I made a mistake. So lambda is equal to, if we use the quadratic equation, then what do we get? Say what the form would be if I just substitute the numbers inside of it without reducing.
So 4 plus or minus square root of 16.
Yeah. Minus what?
20.
Good. And then divided by
2.
Good. So what we get then is 4 plus or minus 2i divided by 2. So that's 2 plus or minus I, right? Okay. So now we have this part. So the solutions are what?
Would it be x squared?
Yep.
Cosine
Times.
log of x.
Yeah. Beta is 1 in this case. Plus d, and then what do I change?
It's just cosine to sine.
Yep.
Also,
Good.
is log interchangeable with natural log in this case, or no?
So in this course from the beginning, I do not like the abbreviation ln. So my conventions are that this is by definition log, right? Because what would log mean? I mean, some engineers say that log means base 10, but that has no connection to mathematics whatsoever because 10 is so arbitrary. So the only base that it makes sense to consider the log is the natural one. So that it's the solution of the differential equation, for example, y prime is 1 over x.
Okay,
So log is always natural logarithm.
okay.
Similarly, there are a few other conventions that I'm using. I'll write things like arc sine instead of sine inverse because this notation is confusing. You could potentially mean the reciprocal. So that's the other convention. That's not necessarily universally adopted. Okay, so Euler equations, they're basically the same as before. We're just solving a different polynomial. And now I'm going to do something completely different. So now I'm going to talk about linear algebra. So first off, I'm going to not be rigorous here, and I'm not going to say math definitions. And I say this as very much a pure math person. So I can be precise, but I'm not going to be precise. I'm going to say a vector space looks like Rn. So there are a bunch of things that are wrong with this sentence. First off, why is the vector space finite dimensional? Second off, why is it a real vector space? But whatever. So what structure do we have in R to the n? In R to the n, which has as points. So we traditionally write them as V for a vector. And then we traditionally write them in a column. And so it would just be x1 through to xn, and those are the coordinates of the vector. So typically, if we just have a real n tuple, we'd write something like x1, xn. That's just an n tuple. But in linear algebra, we're going to write it as a column vector form type thing. And so what structure do we have? If we have W, if also W is equal to, let's say, y1 through yn, then we can add things, and we can also scale W by a number. So let's say this is just a number. It's not a vector, it's a number. And so what should the definition be? It's going to be a vector whose components are going to be, what's the first component going to be?
x1 plus lambda y1.
Yeah. And so that's going to be the general form of it. Cool. Okay. So the point is that in a vector space, we can add and scale. And also we're going to assume that our vector space is spanned by n items. So let's E1 be 1 and then zeros. En be zeros and then 1. If it's an n-dimensional vector space, so in Rn. And EI just be this. Where this is the ith position. And these are known as elementary vectors. Or elementary, yeah. You can also call them members of the standard basis for the space. That's another way of saying it. Okay, so now that we know what a vector is, it's just a list of numbers. Sure, we're not being rigorous. We're not doing like pure math, linear algebra. Vectors, just a list of numbers. Why not? Now what we're going to do is suppose v now in general, maybe it's not a list of numbers, maybe it's a list of indices about let's suppose we have a bunch of linearly independent equations and we're considering the space of all linear combinations of those linearly independent equations. Then that's however many equations you have is basically however many coefficients you have, but it doesn't like look like a list of numbers. It looks like a bunch of functions which happen to come from a list of numbers. So you can have that as well. Now, suppose V is a n-dimensional vector space. So elements are given by lists of n numbers. And then I'm going to suppose that d is going to be a function from Vn into the real numbers. So what is Vn? Vn is equal to V times V, so n copies. And so what I mean by this is that d of n vectors is a number. So I have a function that takes n different vectors and returns a number. And this function satisfies some properties. And the first property is that if I consider, let's say, d, and how am I going to write this? Am I going to write this in a very abstract? Okay, I'm going to write it in a very abstract way. If I have v1, and then I have some position vi, and then later on I have some position vj, and then this goes up to vn. What happens if I swap these two arguments? So if I swap these arguments, the sign of d changes. And a function satisfying this property is known as an alternating function. And the second property that d is going to satisfy is that if I take d, and I'm only going to state this in the first position, and it'll be true in every other position because we can swap, and then we can swap back. So let's suppose that I have v1 plus lambda w1. And then I just have v2, and then I go up to vn. So suppose that in the first position, it's a sum. Then the way that it should behave is that this is just dv1, v2 up to vn, plus lambda d w1, v2 up to vn. So in other words, if you have sum or a linear combination of things in one of the components, then you can distribute it. And since this happens in each component individually, this is known as a multilinear function. So I guess I'll write that in green. Okay, now there's one thing that I could consider. So now consider d of E1 through to En. So now I'm going to plug in the elementary numbers inside of here. And let's suppose that that's equal to alpha. Then the fact that D satisfies these two properties and the fact that alpha is a specific number determine what this function is entirely. So in other words, I'm going to define some very complex function. But if you think about what this function is, I can give it a perfectly precise mathematical definition. It's not clear that this specifies a unique function right off the top of the bat, but it's an alternating multilinear function that takes n arguments in an n-dimensional vector space and returns a real number. And so what this function is it's going to be a multiple of what? So D is alpha times, let's see, does anyone know what's the name of the thing is? Okay, no, it's the determinants. Then D of V1 through Vn is equal to alpha times the determinants of V1 through to, no commas, Vn, where this is known as the determinants. And the determinant satisfies the property so if D is the determinants, then that's equal to alpha times the determinant. So alpha is 1. So the determinant has that if you put in the elementary vectors, then you get 1. So that's how so the determinant is uniquely specified by the being alternating multilinear and being 1 on the units basis. So I'm going to say alternating multilinear function D from Vn to R with D of E1 through to En equals 1. Okay, so let's just look at some properties of the determinants. Well, let's suppose that we consider, so I'm going to, let's D denote the determinant as well, as opposed including this notation. Or you know what? No, let's just D denotes anything satisfying these two properties. If D has these properties, then D of V1, V2, and then what I'm going to do is I'm going to take VI and I'm going to add V1 to it, or I'm going to add lambda V1 to it. So what I've taken is I've taken a list of numbers and then I've added a multiple of the first one to some other position, right? So what does multilinearity tell me that this is equal to?
D of V1 all the way to Vn plus lambda times times, well, now it's all you switched the Vi for V1.
Now, what can you tell me about this expression right here? Using the alternating rule. So what happens if I switch V1 with V1? Then what do I get?
Oh, so it has to be 0.
Yeah, because it's equal to negative itself, right? But I switch V1 with V1. But if it's equal to negative itself, then it has to be 0 because 0 is the only number that equals negative itself, right? So in other words, this has to go away. So in other words, if I take the determinant and I add any multiple of any of one of the items to any other item, it actually does not change the value of the determinant. Okay, so let's use these properties to figure out what the determinant should be in the case of a two-dimensional vector space.
When you're listing like D, V1 to Vn, like, are we imagining each of the V's as columns or as rows?
So each of the V's is going to be a column. Now, so in a two-dimensional vector space, the determinant is really going to be, I guess in my notation, it's going to be the determinant of two column vectors. However, the way that we'll write that is just the determinant of the numbers A, B, C, and D, right? Now, what I have is that I can split A and B. AB is equal to A0. That's a 0. Plus 0B, right? So by multilinearity, this is equal to A0 CD plus 0B CD. And so that's equal to, well, then splitting up the last thing further, A0 C0 plus A0 0D plus 0B C0. Okay. These suddenly started looking like matrices, whereas I want determinants on this. There was a 0 here. Okay. Now, oh, I guess there's one more thing that I can say. Oh, cool. Yeah, that's cool. That's cool. So I'm going to actually, before I do any of this, I'm going to establish one more property. Suppose that I have D, and then suppose that I have 0 here, and then I have V2 up through Vn. So what I can do then is I can add any multiple of V2 to 0, because this argument applies for not just moving V1 into position, but moving V2 into V1. So that's equal to D of V2, V2, right? but there's now 2 copies of V2. And so did I show you that before? If there's a repeated thing, before we saw that it was 0, so it's equal to 0. So if any of the entries are 0, then it has to equal 0. I guess there's another way of proving it. 0 is 0 plus 0, right? So we can distribute that as being D0. So then subtracting D0 from both sides, we get that this expression is 0. So that's 2 separate proofs of that fact. Okay, so the point is that if we have an expression like this, then we can subtract some copy of this times this. So for example, let's say this is equal to star. So note that A0 C0 is equal to A0, and then here I'm going to have C minus A times, or rather, C over A times A. And then here I'm going to have 0 minus C over A times 0. So what I've done is I've taken this column and I've subtracted a suitable multiple of it from this column. And because doing that doesn't change what the determinant is, this is the same as the determinant of A0, 0, 0. And because there's a 0 column here, that's 0, right? So in other words, what I can conclude is that this thing and this thing are both 0. And also, so going back here, by multilinearity, if I have a column multiplied by a number, I can pull out that number out front. So in fact, this thing, I can pull out AD out front, because this column is multiplied by A and this column is multiplied by D, and get 1, 0, 0, 1. And then from this one, I can pull out a C BC, and then gets 0, 1, 1, 0, right? Now I can swap these 2 columns. At the penalty of a minus sign. But this is the standard basis. So both of these things are equal to 1. Okay, so what we've discovered is that if we have a function that's multilinear and alternating, it takes the unit value and supply the elementary basis, then on a 2-dimensional vector space, it has to be given by this formula. So results. A, B, C, D. The determinant is AD minus BC. And the way that you think about this is think you have A, D, and you have B, C. And you're going to do plus this minus this. So it's going to be diagonals in both cases. So AD minus CB or BC. And now I am going to spare you the process figuring out how to compute the determinants of a 3x3 matrix using this process. This process was very exhausting, but you can do the same thing and you can get what the formula for a 3x3 determinant is. And I can tell you what that is. So if I have x11, x21, x31, x, and so we're going to need only 2x2 and 3x3 determinants in this class. So what you do is I'm going to let the green things be positive. So I'm going to do this edge and this edge. Then I'm going to do this edge, and then this one is going to go through the wall and go through here. Like Pac-Man teleporting through the side of the screen and appearing on the other side. Then this one is going to go through here, and then this one is going to go through here. So they're all the diagonals with teleportation through the walls. And then you're going to go all of the diagonals in the other direction. So this is going to go here, and this is going to go here. Then this is going to go here, and this is going to go here. Then this is going to go here, and that is going to go there. And so all of the green chains, they get a plus sign, and all of the red chains, they get a minus sign. And so what you get as a result is I'm going to write it down basically once, but you remember this picture. So I'm going to write x11, x22, x33. So that's this line. And then I'm going to subtract the other thing, minus x11, and then x23, x32. Then here I'm going to get x12, x23, x31. So that's the red thing. Sorry, that's the green thing going in the second thing. Then I'm going to do the red thing going from the second thing, minus x12, x21, x33. And then I'm going to do the green thing from the last thing, which is x13, x21, and then x32. And then minus, and then the red thing from the last thing, x13, x22, x31. So when you have a 3x3 matrix, the determinant is given by this formula. Do not memorize the indices of this formula, just memorize the fact that it's diagonals in this way are green and diagonals in that way are red, right? And so you could derive this formula by a process similar to this one, but it would be very painful and exhausting. But you can sort of see how you'd be able to get that out of that, right? And so you can also derive a general formula for determinants of n by n matrices, but we'll only be using 2x2 matrices and 3x3 matrices in this class. Linear algebra is not a prerequisite for this course. And what did I assume about linear algebra? Nothing. I just told you that vectors are lists of numbers. You can add lists of numbers. You can scale lists of numbers. And then there's this magic property function that takes n vectors. And that's one on the unit basis, where the unit basis are these elementary vectors with a 1 in the ith position. And then I said that, well, if you have that function satisfying that properties, I could tell you what the formula for it is for two-dimensional vector space. And then here's what the formula is for three-dimensional vector space, right? Okay, so now we know determinants. That's cool. Good. Oh, so it's 8:04. I'm going to prepare a bit more material. So I'm going to take, let's say, a 10 or 15-minute break. You know what? I'll do 10 minutes because it's already 8:04. So let's resume at 8:15. Okay. Okay. Let's see. Right, so we reviewed determinants, and now I'm going to introduce a very special determinant called the Wronskian. So what the Wronskian is that given n functions, y1 through to yn, that's have derivatives of order n minus 1. Consider the determinant. So we're going to put, this is going to be a function of x. So the Wronskian of y1 through to yn is going to be a function of x. And that function of x is it's going to be at every point the determinants of y1 of x, y2 of x, I guess I'll write, up through yn of x. Then here I'm going to put the first derivative of y1 of x through to the first derivative of yn of x, all the way through to the, what derivative am I going to go up to in order to make this an n by n column?
N minus 1.
Yeah, because I start off at 0, so and I want n things. So I'm going to put at x, I get a bunch of numbers. I get the values of all of the functions, and I get the values of all of the derivatives, and then I get the value of all their minus 1 derivatives. Then I put that into a big table, and then I take the determinant of that. And so that's going to be a function of x, right? So in particular, the Wronskian of two functions, y1 and y2, I'm not going to write the x arguments. Well, so y1 does not get a derivative in the positive thing. So I get y1 times y2 prime minus y1 prime times y2. So that's the determinant of this 2 by 2 matrix where I put the first derivatives of the functions there. Now, here's the deal. This is going to be really cool. Suppose we have a second order linear homogeneous ODE. And so the general linear second order homogeneous ODE is y prime prime plus f of x, y prime plus g of x, y is equal to 0, right? And suppose this has solutions. Y1 and y2. Then what's going to happen is I'm going to consider the Wronskian of y1 and y2. And that's what I have above. And now I'm going to, this is a function of x. I'm going to take the derivative of it with respect to x. So what do I get? Product rule, I get this.
y1, y2 double prime. Plus y1 prime, y2 prime. Minus y1 double prime, y2. Minus y1 prime, y2 prime.
Yeah, now the y1 prime, y2 prime, those cancel out. So I get y1, y2 double prime minus y1 prime, y2. Sorry, now the double prime is on the y1 rather. Now, however, we know something about y1 and y2. What do we know about y1 and y2?
That they're both solutions.
Yes, so in particular, y2 double prime can be rewritten in terms of its lower derivatives as well.
Minus g of x, y minus f of x, y prime.
Sure, you can switch the order. That's fine. G of x, so it's going to be minus g of y1 minus f of y1 prime, right? And then we're going to get minus, and then we're going to do that expansion here, minus g of y. Sorry, this is a y2. I want y2s here because g y1 minus f y1 prime times y2. Nope, I did need to actually break it up. Okay. And so as a consequence, let's look at, for example, the y1 g y2 term. Those don't have derivatives, right? And this term cancels with this term, right? So what I get overall, because there's a g, there's a y1, there's a y2, there's a g, there's a y1, there's a y2, except there's a negative sign here. Well, there's negative signs here, but there's a negative sign here. So this one has the opposite sign from that one, so they cancel out. So what I get overall is that I get, let's see, what term is going to be positive? This term is going to be positive. It's going to be f y1 prime y2 minus f y1 y2 prime. But if we look at what the Wronskian is, it's y1 times y2 prime, right? So what this is actually is it's negative f times the Wronskian of y1, y2. But what does this tell us about the Wronskian? It tells us that the Wronskian satisfies what kind of differential equation?
Separable.
Exactly. So W satisfies dw dx is equal to negative fw. This is sort of like the key insight. And so we don't know what the two solutions of the equation are, but we do know what the Wronskian is. So if I do this, I get dw over w, and this is the equation that you should memorize. So this is the equation that you used. dw over w is negative f dx. And so as a consequence, you get that log of w is equal to negative integral f of x dx. And so as a consequence, we get that w is equal to C e to the negative integral f of x dx. Okay, so let's think about what this means. Remember that y1 and y2 were two arbitrary functions, right? Well, what happens, for example, if I change the order of y1 and y2? If I swap them, then what happens to the Wronskian?
Would be multiplied by -1.
Yeah, so it changes sign. Now, what if I took a solution that was a multiple? What if I took y1 and then I took a multiple of y1? Then what would happen to the determinants? Two columns would be multiples of each other, right? So what would the value be?
Sierra?
Yeah. So the thing about the Wronskian is that it depends on what functions I take, right? And that's going to give me this constant. However, the cool thing is that sort of if it's 0, then it's 0. But if it's not 0, then it's a multiple of this specific function. And then I can just change them in various ways, and it's still going to be a multiple of this function. And what's really cool about this function? This function is the exponential of something, right? And what can you tell me about the exponential? Do exponentials have zeros? Right. So if we think about the graph of the exponential, it doesn't have any zeros, right? So what we conclude is that for solutions y1 and y2, the Wronskian w y1 y2 is either uniformly 0. For example, if y1 is equal to y2, it will be uniformly 0. And when I say uniformly, I mean it's a function of x. So I mean as a function of x, it will be 0 everywhere, or uniformly non-zero. Now, observation. If y1 and y2 are linearly dependent, then the Wronskian is 0. Now, here's sort of like an annoying example. Suppose that y1 looks like this. So y1 is 0 everywhere except for the fact that it's not 0 here, right? And suppose that y2 looks like this. It's 0 everywhere except it's not 0 here. So in mathematics, we'd say that y1 and y2 have disjoint support, right? If y1 and y2 have disjoint support, then because this is uniformly 0 here and its derivative is uniformly 0, at these points, y2 would have 0 for its value in its derivative, and here y1 would have, so the Wronskian of these two functions is going to be 0, despite the fact that it's not the case that one function is a multiple of the other, right? However, if y1 and y2 are solutions of a specific differential equation, then the Wronskian being 0 implies that y1 and y2 are linearly dependent. So in general, the Wronskian being 0 does not imply that two functions are linearly dependent. For example, this disjoint support example. However, if the functions come from solutions of a differential equation, then in fact, the Wronskian being 0 is exactly a test for whether those solutions are linearly independent or not. So this is going to be a fact. I'm just going to assume this. Okay, so that's pretty cool. So then basically what happens is if you take two linearly independent solutions, and remember the theorem from the start of the class, if you have a second order linear homogeneous equation, there are two linearly independent solutions and every solution is a span of those. Well, if you take the Wronskian of any two linearly independent solution, then you'll get some multiple of this function right here. So in other words, you can find the Wronskian of two linearly independent solutions. That's something that you're able to do without knowing what those two solutions are. And so sort of the state of affairs, it's not exactly an ideal state of affairs. Well, actually, before I say the state of affairs, I'll give an example. Actually, it's not an example. First, it's going to be a process. Suppose that's y1 is a solution of y prime prime plus f y prime plus g is equal of y is equal to 0. Then I can find a complementary solution y2. So I'm going to show you that if I know one solution, then I'm able to find a linearly independent solution from it. And this is going to be using the Wronskian trick. So how do I do this? Well, this is actually a pretty neat trick. So the Wronskian of, so we're going to solve for y2. The Wronskian is equal to y1 y2 prime minus y2 y1 prime for some solution y2. And then I'm going to divide everything by y1 squared. And what does this expression here equal?
It looks like a quotient rule.
Exactly. So what function would I be? What function would I have at the top?
I would like to, is it y2 over y1?
Yeah.
Oh, yeah.
So by the way, when I teach calculus A, I tell my students not to memorize the quotient rule because it just follows from product rule, right? This is literally the only example that I know in the entirety of mathematics where the quotient rule is actually useful to know. That's it. Okay, that's it. Okay, that we have finished getting our utility from the quotient rule. Let me make this bigger. Well, okay, this is great. Because what it tells us then is what? It tells us then that this is going to be some function of x, right? So y2 over y1 is equal to, this is, I guess, a separable equation for this quantity. It's equal to the integral of the Wronskian over y1 squared dx, right? And so that tells us that y2 is equal to y1 times the integral of the Wronskian over y1 squared dx. Now, what is the Wronskian? Remember that the Wronskian is only defined up to a multiplicative constant, right? So for example, if I took the Wronskian to be 0, which is the case when y2 is linearly dependent with y1, then I'd be integrating 0 here and I'd essentially get 1. right? So then I get y2 equals y1. However, if I take any non-zero Wronskian, then I will in fact get a non-trivial function here. And so I will in fact get a linearly independent function from y1. So the state of affairs is going to be that if we have a second order homogeneous linear equation, we are unfortunately not going to be in as good a position as we had for first order equations, because for first order equations, I gave you a process for solving it. So for the homogeneous equation, it just became separable, right? After doing some stuff. But unfortunately, I won't give a method for being able to solve for the general solutions. If they're constant coefficient, then great. We just solve a polynomial and we're done. But if they're arbitrary functions, then there isn't a nice method for finding it in general. But if you know one solution, then you can get the other solution. And so I'll give you an example of that. So I'm going to consider the example x minus 1, y prime prime minus x y prime plus y is equal to 0. So by inspection, there's actually, notice that there's basically, there's a bit of a symmetry here. So can you guess what's one of the solutions is? So notice that, let's imagine that all of the primes went away. If all of the primes went away, then I'd have x minus 1 here, and then I'd have minus x, and then I'd have 1 here, right? And then it would be 0. So what would make all of the primes go away?
Oh, if it was e to the x.
Yeah. So if y is e to the x, then this is a solution. And then the reason is exactly, that's good. Good on you. Because as x minus 1 e to the x minus x e to the x plus e to the x is equal to 0, right? So we're able to find one solution. But now we're going to use this process to find the other solution. So first off, this function, it has an x minus 1 out front, right? But the way that I've been writing it is I've been writing it with a coefficient of 1 here. So I'm going to divide, I guess, this equation is really y prime prime minus x over x minus 1 y prime plus 1 over x minus 1 y is equal to 0. Now, let's remember what the equation for the Wronskian is. Thus, it's going to be the derivative of the Wronskian divided by the Wronskian is equal to negative f. And so negative f in this case is x over x minus 1. So this is the equation that I told you to memorize one equation. The equation was from all of this. It's the equation d Wronskian dx is equal to negative f times the Wronskian. And so in particular, you rearrange this to the equation that you have below. D Wronskian over Wronskian is negative f dx. Okay, so in other words, the logarithm of the Wronskian is equal to the integral of x over x minus 1 dx. And what do I do to this integral?
Partial fraction.
Right, so if I subtract something from the denominator, I'm going to subtract an x minus 1 from here, right? So I'll get 1, and then what will I get if I subtract x minus 1 from x?
Plus 1 over x minus 1.
Good. And that's easy to integrate. What do I get?
X plus oh yeah. So log x minus 1.
Good. And as a consequence, that's what the logarithm of the Wronskian is. So what is the Wronskian? I mean, I could add, I'm not going to care about constants. I just want some Wronskian because I want some complementary solution, not the general complementary solution. So when I exponentiate this, what do I get? How does it simplify?
X minus 1 times e to the x.
Exactly. So we split this up into two multiplicative factors. E to this is x minus 1, and then I have the e to the x. Okay, so now let's remember what the process was. From before, then we saw that y2 was y1 times the integral of the Wronskian divided by y1 squared dx. Thus, we have y2 is equal to y1 times the integral of the Wronskian divided by, let's see how I am for time. Okay, I'm good for time. I'll exactly be able to solve this problem. By y1 squared, y1 was e to the x. So e to the 2x. And y1 is e to the x. So that's equal to, I guess we'll have an e to the x floating around this entire calculation. And what are we going to do to solve this integral?
By parts?
Right, so which one of these factors do I want to differentiate and which one do I want to integrate?
The x minus 1 you want to differentiate.
Yes, so I would write in the notation that I did in the first lecture is that f is equal to x minus 1. And then that's dg is equal to e to the negative x dx. As a consequence, what is df?
One.
Yeah, so a df is going to be dx. And then when I integrate this, what do I get? Chain rule?
Minus e to the negative x.
Exactly. Okay, so remember that we have this e to the x floating out front. We should be careful not to forget that. So we have e to the x. Then we do the cross term, which is going to be, I guess, negative e to the x. And then we multiply x minus 1 by e to the negative x. And then that minus sign is out front. And then we're going to do minus this cross term. Except for the fact that there is already a minus here, so it's going to be plus, then let's not forget our e to the x out front. You know what? It might actually be clearer if I kept the e to the x here and then did this. And then I do this cross term. So they, well, that's not hard. So we already did this integral. It's negative e to the negative x. So I get e to the x times negative x minus 1 e to the negative x. And again, I only want a particular complementary solution. So I'm going to ignore constants. Minus e to the minus x. Okay, look, here's e to the minus x. There's minus signs, and then there's a minus sign here. There's no minus sign here. So these two terms will cancel out. So what I'm going to get overall is just the minus x e to the x times e to the negative x, which is just negative x, right? So in particular, that's my value for y2. Now the negative sign doesn't matter. So the general solutions are c times y1, which is e to the x, and then plus d, and then negative x, I'll absorb that into the constant dx. That's the nice way to write what the solution is. So here we were able to use this process of knowing what the Wronskian is, and then how to get the second solution in terms of this first solution to just make this observation, which was, I guess, easier than observing that maybe x is a solution to this. Maybe it's not that hard to observe that x is a solution to this, because both of these, this would become 1, and then this would be x, and it'd be x minus x. So, okay, it was just as easy to observe that. But anyway, it was a worthwhile exercise still, because it applied that method. So what can I tell you about the solutions y1 and y2?
You're muted.
Yes, sorry, there was an internet connection from my end. Yes, a disconnection. Wait, why did it? Yeah, because it reconnected. Apparently it mutes me when I reconnect. That's weird. Okay, but thanks. So what was the last thing that you heard? You heard me finish this example, right? Good. Okay, so again, what's the lesson? We have the Wronskian. We can find from the differential equation what the Wronskian is, but that doesn't in general let us solve for y1 and y2 from the equation. So that's going to be something that's not always going to be possible. But if we can find one, we can find the other. And we're going to use the Wronskian a lot, because what we're actually going to do next time so if I have that's y1 and y2 are linearly independent solutions of the homogeneous equation y prime prime plus f y prime plus g y is equal to 0, then using the Wronskian and other techniques, I will always be able to solve the inhomogeneous equation. So that's pretty cool. So I'm going to give you a way for solving inhomogeneous equations from homogeneous equations, assuming that you know the solutions to the homogeneous system. So that's going to be the key thing. So basically, when it comes to the theory of linear second order differential equations, the question that you want to ask yourself is, can I find at least one solution to the homogeneous equation? And if you can find at least one solution, you can find two solutions. If the coefficients are constant, then it's very easy to find what the solutions to the homogeneous equation are. And then if you can solve the homogeneous equation, then you can also solve all inhomogeneous equations. and that's going to be pretty good. So it is 8:50, and that's a bit early, but that's what I have for today. I am going to try and actually do the assignments. The assignment will definitely be with, I'm going to fix the one typo and then add one question. And that's definitely going to be in your inbox by the start of next lecture, hopefully by midnight. Hopefully I do it now.
Also,
Cool.
can you
So
post
what
the
did we
note?
learn today? What we learned today was that we started at the end of last lecture, the theory of second order ODEs, and we were specifically, well, so we had this general results that the solution is going to be a two-dimensional vector space. So there are going to be two solutions that are multiples of one another, so that the general solution is exactly all linear combinations of those. Then we said, well, what if we have a constant coefficient differential equation? Well, then using the theorem and being able to solve quadratics actually gives me a process for being able to identify two linearly independent solutions in all three cases. So therefore, I can solve the homogeneous equation for all constant coefficient second order equations. Okay, cool. So then we talked about Euler equations, which was basically the same thing, except for the fact that you move one coefficient over to the other, and then the process for writing down the solutions is a bit different. And then we started talking about linear algebra. You don't have to understand linear algebra, you just have to be able to do computations, right? Okay, vector is great. There is this function that's the determinant, it satisfies some properties. I was able to derive what the function is for two-dimensional vector spaces from the properties, but all that you remember is it's just diagonals in the 2 and the 3-dimensional case. And we're going to use 2 and 3-dimensional determinants in our computations. Then a particular determinant is the Wronskian. And the cool thing about linear equations is that you can actually get a separable equation in order to solve for the Wronskian. And that's going to be very useful. So in particular, for example, it's going to give us a way for finding a second solution. If we have a first solution, then it's going to let us next class solve the inhomogeneous problem. Cool. So I will see you tomorrow then.
Can you also like post the notes from last class? Can you email them to us?
Yeah, thank you. Thanks for the reminder. And I'll do the video, notes and video from last time, and then this time, and then assignments update.
Thank you.
Good.
Thank you. Have a good day.
Thanks for the reminder. Have a nice day. Bye.